Greetings and welcome to Computer Science 221. We have great stuff for you today, just hold on. Okay, today we're going to talk about something really cool. It's called the SR flip-flop. Sometimes it's referred to as the latch, the SR latch. All of the circuits that we've considered up to now have been examples of what are called combinatorial circuits. And what that means, there have been a bunch of AND gates, there have been a bunch of OR gates, NOT gates. And what has happened is the output is purely a function of the input. What we're going to consider now are what are called sequential circuits. And they're going to be a little bit different. In sequential circuits, the output is a function of the input and, here's the key part, a state. That's almost like saying something like the following: that the circuit might behave differently at night than it does during the day. Or it might behave differently if it's hungry or if it's full. I know that sounds a little bit strange, but let's go through and we'll consider an example of this and then we can discuss it a little bit further. Now, our initial introduction to sequential circuits is going to be this thing called an SR flip-flop. And it's going to look a little bit strange from what we have seen before, in the sense that it's going to be a feedback circuit. And first of all, it's constructed out of two NAND gates. And here's the part that's going to look kind of weird to you. So we're going to have an input over here that's called S, and we are going to have an input over here that is called R, but here's the part that's really strange. We've got A over here, and over here we've got B. And you'll notice that what happens is the output of one of these NAND gates is actually the input to another. This is really kind of strange. This is sometimes what's referred to as a feedback loop. And it's not exactly clear how this circuit behaves. So what we need to do here is we need to analyze this. Turns out there are going to be several different possibilities here. But for example, I want to consider the following. Suppose S is equal to 1, and suppose that R is equal to 1. And I also want to suppose that A is equal to 1. Okay? Now, if A is equal to 1, okay, then what I have going in here is there's a 1 going in here, and there's a 1 going in here. It's going into a NAND gate. So what that means is that B would become 0. And then a 0 is coming in here. And I've got a 0 and a 1 coming in here. And a 0 and 1 going into a NAND gate is going to have a 1 coming out of here. Okay? So again, you can now feed this back. If I have a 1 going in here and a 1 going in here, it's 0. Everything is stable. The point is what's going to happen here is B is going to become 0. And everything else just stays the same. Now the other situation I want to consider here is I want to suppose S is equal to 1 and R is equal to 1. And now I want to assume that A is equal to 0. So if I do that, let me come over here and erase things. Okay, so if I'm assuming that A is equal to 0, then I'm going to come over here and I'm going to have a 0 here, and I'm going to have a 1 here. And putting a 0 and 1 into an AND gate is going to make B a 1. And I come back over here, and this is going to be a 1, and this is going to be a 1, and a 1 and a 1 going into a NAND gate. The A is going to stay a 0, and we can see that the whole thing is stabilized. So what's going to happen over here, in this situation here, is this B would become 1, and everything else is stabilized. Okay? Well, we're not done. We have a lot more analysis to do here. Now I want to consider, suppose S is equal to 1, and R is equal to 0, and A is equal to 1. So what I got to do is come over here and let's erase these. All right. So now A is 1. So I've come over here and I've got a 1 here, and we have an R is 0. So a 0 and a 1 going into a NAND gate, what's going to happen there? 0 and 1 going into a NAND gate, well 0 and 1 is 0. It's going to make this a 1. Okay, and I come over here and now this is going to become a 1. And S is 1. And a 1 and a 1 going into a NAND gate is going to make this a 0. And I come over here, so now this is a 0. And now a 0 and a 0 going into a NAND gate, this is a 1, and it looks like now things have stabilized. Okay, so what's going to happen over here in this situation is A is going to become 0, and B is going to become 1. I hope everyone followed that. I want you to notice, and this is going to happen, we have a few more examples to give. Notice that A and B always turn out to be just the opposite of each other. Okay, if A is 1, B is 0. Here, A is 0, B is 1. Here, A started out to be 1, but it became 0, and B was 1. Let's consider this situation now, where I do S is equal to 1, R is equal to 0, and now A is equal to 0. And let me go ahead and first erase everything over in here. Okay, so now let's work this example through. So in this case, S is 1, R is 0. We said initially A was 0. So I've got a 0 over here, and a 0 and a 0 going into a NAND gate is going to make B a 1. And I put a 1 over here, and a 1 plus 1 going in here means A is 0. And it looks like we have stabilized, and this is going to set B equal to 1. Okay? So now we had S1, R1, S1, R0. Let's do S equals 0. R equals 1, and let's let A equal 1. And let's work that through. Okay, so A is 1, and we said S was 0, and R was 1. So now I have a 1 and a 1 coming in here into a NAND gate is going to make that a 0. And now I have a 0 and a 0 going in here, and that's going to make it a 1. And it looks like we have stabilized, and that makes b equal to 0. And now I'm going to let s equal 0. I'm going to let r equal 1. And I'm going to let a equal 0. And let's work this one through. All right, so we have s is 0, we have r is 1, we have a is 0. So I come over here and I have a 0 and a 1 going into an AND gate. That's going to make this a 1. I come over here, that's going to make this a 1. A 0 and a 1 going in here is going to make this a 1. So now this is 1. And I come down here and I erase this. And now this is a 1. And I have a 1 and a 1 going in here, so it's going to make b 0. And now that's going to make this a 0. And 0 going in there is a 1. And now this is all stabilized. So what has happened over here is a has become 1 and b has become 0. Okay? So now the only thing left is what happens if s is 0 and r is 0. And the answer is this is bad. Don't let it happen. And I will leave it as an exercise for you to see what happens if you let these both be 0. I think you will find that this thing doesn't ever get into any steady state. But now let's go back here and take a look at what this all does here. It turns out, first of all, we define the state is the output of A. So what we want you to notice here is that first of all, in this situation right over here, when s is equal to 1 and r is equal to 1, the state doesn't change. In other words, if s is 1 and r is 1 and a is 1, after we went through everything, a was still 1. Likewise, when s was 1 and r was 1 and a is 0, when we went through all the calculations and we got into a steady state, a was 0. So we say that when s is 1 and r is 1, the state does not change. Now what happens over here in this situation when s is 1 and r is 0, we can see what happened here. A went from 1 to 0, and here when it was in 0, it stayed at 0. So what we're going to do is we will say here it clears the state. Okay? In other words, no matter what state A starts in, when s is set to 1 and r is set to 0, we ultimately end up with a at 0. It's clearing the state. Likewise, we can see over in this situation over here, regardless of how a started, okay, if we let s equal 0 and r equal 1, when we're all done, a is always 1, so this sets the state. So basically, we can make the following little table here about the SR latch. And we can say Okay, so we said over here, let's summarize this. We said that when S is 1 and R is 1, when we're in the situation of 1, 1, there is no change. And we said that when, let's see, when S is 1 and R is 0, it clears. When S is 1 and R is 0, it clears the state. And clearing the state means that we set the state equal to 0. Okay? The other thing is we can say that when S is 0 and R is 1, it sets the state. And this one over here, I'm going to put a big X through, meaning you don't ever want it to happen. Okay? So remember, what's going on here in these latches, there always is an output, and a lot of times in the literature they'll refer to the output, the state of it, as Q, and then there's also Q prime. This is the same thing that we've called A and B. So in other words, you'll sometimes see people write it this way. They'll come over here and there'll be S and there'll be R, and then there's an output Q and there's an output Q prime. So these guys over here are always inverses of each other. Q represents the state of the latch. Okay? Okay, so with the SR latch out of the way, we're going to do one more thing. This is going to look scary at first. It isn't. We're going to come up with something that's called a D latch. And the reason why it's called a D latch is this is sometimes referred to as a data latch. And this thing over here, this really is the foundation of all of computer memory. So watch closely. Remember, we had this thing before that looked like this. We had this NAND gate over here. And here's A. We had this NAND gate over here. And this was B. And remember, this guy came back in this way. And this guy came over this way. And then we had this line over here. And we called this S. We had a line coming over here called R. But now what I want to do is I want to have another NAND gate here. Like that. And what's going to happen is I am going to have something over here. And this is going to be called WE. And I'll tell you what that stands for in a little bit. And over here there's going to be something that I'm going to call D. And D will go right into there. And I'll come over here. And here I'll invert it. And I'm thinking at this point you're all looking at it going, oh my goodness, what is going on here? Well, okay, let's analyze this. And believe me, when we're all done, you're going to see that this thing is a whole lot simpler and nicer than it looks right now. So here are a couple of supposes here. Suppose D is equal to 1 and WE is equal to 0. Now, first of all, if D is equal to 1 and WE is equal to 0, I have a 1 and a 0 going in here. And if I have a 1 and a 0 going into a NAND gate, what's coming out of here, remember, a 1 and a 0, 1 and 0 would be 0, so NAND would be a 1. Likewise, what would be going on in here if WE is a 0 and DE is a 1, what I have going in here would be 0, 0, and 0 and 0 is 0, and this is a 1. So notice now what I have, when this is true, then I have S is equal to 1, and R is equal to 1. And you may recall when S is equal to 1 and R is equal to 1, there is no change. Okay? Suppose D is equal to 1 and WE is equal to 1. Well, let me go ahead here and erase things a little bit. Okay, so first of all, if D and WE are both equal to 1, I have 1 and a 1 going into a NAND gate, and that's going to make S 0. Okay? Likewise, if I have D as 1, I'm going to have a 0 going in here, and I have a 0 and a 1 going in there. Remember, if I have a 0 and 1 would be 0, but if I NAND it, it's a 1. Okay, so when S is 0 and R is 1, when S is 0 and R is 1, I'm setting the state. So what that means over here, S is 0 and R is 1, I'm setting. Which means that A is equal to 1. Okay? Likewise, if I come over here and D is equal to 0 and WE is equal to 0, let's see what that's going to do. Okay, if D is 0 and WE is 0, I have a 0 and a 0 going in here, which is going to make this a 1. And if I come over here, I'd have a 0 and a 1 going there, which is going to make this a 1. Which means S is equal to 1, and R is equal to 1, and that means no change. Okay? And the last situation I need to consider is what happens if D is equal to 0 and WE is equal to 1. So let me just go ahead and erase things over here. And what's going to happen in that case, I'd have a 0 and a 1 going in here. That's going to make this a 1. Did I get that correct? If D is 0 and W, and if I come over here, I'm going to get a, let's see, if D is 0, there's a 1 going in there, and there's a 1 going in there. That's going to make this a 0. So now I have S is equal to 1, and R is equal to 0. And when S is equal to 1 and R is equal to 0, that's clearing the state. Which means A is equal to 0. Okay, so what did all of this mean? Well, first of all, WE stands for what's called write enable. And the first thing that you can see is that in the situations where write enable is set to 0, okay, nothing happened. Okay, the state of this entire circuit stayed exactly the same whenever write enable was 0. On the other hand, when write enable is 1, the state of the circuit was whatever was on D. Okay, when D is 1 and I said write enable is 1, the output of this thing became 1. And when write enable was 1 and D is 0, the output of this thing became 0. This entire thing right over here, this is 1 bit of storage inside a computer. And again, if you want to, schematically, it might just be easiest to think about it this way. Here's a line coming in calling D. Here's a line coming in calling write enabled. And here's the output of it right here, which your author is calling A. Put a 1 on write enable, and this will assume the internal state of this circuit will be whatever you put on D. This is 1 bit of memory storage. Okay? This is very, very important.